So we're talking about multidimensional spaces, starting with dimension 1, 2. So up to 3 dimensions are still, let me review what we did last week. So up to dimension 3, we can still associate these spaces, kind of Cartesian spaces, with geometric or kind of real objects, so line, plane, in our 3D space. But even now, after we introduce the Cartesian system, then, as you can see, locations, points on the line correspond to real numbers each, and that is the reason for the notation that we're going to be using. So real numbers, and then notation is R. Okay, so R is, as you can see, it's not just any R, it's R thick R, and I just write it with a kind of a hollow R. In reality, in the book, you will see it like this. You know, it's just a bald-faced R. So nothing special. It's just when you do it with, by hand, that's how you do it, like this. Okay, but that's what it means. Okay, so indicating, so R stands for real numbers, and then as you proceed to higher dimensions, even though there's a plane, now we know that every location on the plane is associated with a pair of real numbers. Okay, and that's why we use the notation R2. Okay, so the plane is R2. So, well, technically it's not. The plane is R2. It is the correspondence here to locations. Every location on the plane, we correspond here real numbers x, y, and that if you take all of these x, y, then we get R2. Okay, so all possible pairs of real numbers. Okay, and then we do the same with dimension 3. The notation is R3. Once again, all triples. Okay, so and then because the correspondence is, where's the correspondence? Point P corresponds to a triple of real numbers and vice versa, which means, incidentally, probably I should ask you this question, is what do I mean by correspondence here? A correspondence between points on one hand, triples on the other hand. What is the nature of that correspondence?
One-to-one and onto?
One-to-one onto function. Okay, so correspondence is just a fancy word for functions whenever the functions are, it is a nice function, a function, one-to-one onto, one-to-one onto. Okay, so that the vice versa part indicates that it is one-to-one onto, so we can reverse the arrow from points to triples and from triples to points, and we can go back and forth within ambiguity. Okay, so dimension 4, as you can see, it is quadruples, and the notation for it, and then everything beyond is, you can guess what they are, right? So and on. Okay. So they seem unrelated, maybe, but we keep in mind that the relation is not just they contain, say R3 contains 3 copies of R1, right? R3 contains 3 copies of R1 as its axis. Okay, but also, what else does it contain?
R2 and R1?
Say again?
R1 is in R2, is in R3?
So we could say, if that's what you're saying, is that over here, here, the same exact, almost exact sentence can be said about R3, so it contains two copies of R1 as its coordinate axes. Okay? But in addition to that, let me finish with this. So you can do more than that, because you can create like a row of axes like this. So R2, if I repeat my y-axis infinitely many times, I will have R2. Okay, so if this axis is repeated infinitely many times with no overlap. Okay, and similarly, I could go horizontally, and then once again, these are infinitely many copies now, this time. Not as axis, there are only two copies. But if I also go parallel to the axis, I'll have more and more. Okay, and the point is, of course, is not only the visual similarity. Geometry and algebra will be then inherited by R2 from those two copies of R1, as well as from all of these will be also matching. Geometry and algebra R2 will match the geometry of all of these lines that come from R1. Okay, and now furthermore, in R3 is slightly more complicated. Okay, and then as I said, I think three copies of R1 is as coordinate axis. But if I want to do stacks, R3 is a bunch of stacks of what?
R2.
R2. So it has three copies of R2 as its coordinate planes. Okay, and then you can actually stack them up in three ways to create, once again, the three-dimensional space. Like think a book. As simple as that. A book. So you can go this way, right, and you can have a stack of copies of R2, or you can go horizontally like this, and vertically. Which one is left? This one, facing us. Okay, so and once again, so every R2 reappears many times in R3. And that is a way to understand R4, for example, if that comes up. It contains four copies of R1, right? 4 copies of R1 to begin with as axes. But then, so then you can think of it looking like this, roughly. I mean, you can really have a good picture of the 4-dimensional space in 3-dimensional spaces, especially on the plane, which is also 2-dimensional. In fact, so that's a really bad illustration. But well, that's what it is. 4 copies of R1. But also, following this idea, you take what? You take the copies of R3. Okay, and stack them somehow, and that creates a 4-dimensional space. Okay, if you can imagine it, you're good. It's hard. So it's hard, and that's why we primarily, as far as R4 is concerned, beyond relying on quadruples. So it will be more algebraic and than anything else, because we are out of dimensions. Okay, so next is what we started, is the geometry. So given 2 points, what is the distance in terms of the coordinates? So we want to utilize the coordinate system of on the line, plane, space, and so on, so that we wouldn't have to do it from scratch and actually do any actual measuring. Because what is a coordinate system if not a pre-measured plane? Plane or axis, if it is a line, in this case, it is pre-measured. All of those marks on the line are measurements, prior measurements, so that we don't have to measure anymore. Okay, and that's how we get the distance between 2 points is simply the absolute value of the difference. even though that only applies to numbers, because to numbers, meaning that we implicitly, well, actually explicitly, not implicitly, we are using algebra here as well. So not pure geometry, because this is, well, let's say this is geometry. Well, this is algebra. You subtract, right? So algebra. Okay. So simultaneously, you actually have to do both. But let's suppose we're doing geometry right now, and just concerned with distances for the most part. I wanna well, first of all, why do we care? Not only because you want to do geometry for whatever purpose you have, but just if you narrow down to calculus, when did we use this? Not like a long time ago. Distances. Expression similar to this, with absolute value.
What, in the epsilon delta definition?
Yeah, the definition, I'll take instead the definition of a limit of a sequence, because it's calculus 2 and more recent. But other than that, that's exactly, it is the limit. So the definition of the limit, and you certainly know how important it is in calculus. The limit, so say I have a sequence, A and converges to A, by definition it means what? For any epsilon greater than 0, there is an n, such that, and now here it is, an minus A is less than epsilon for all n larger than n capital. Okay, so that's exactly, it reappears. These two things reappear, the geometry, so the absolute value, as well as algebra of subtraction that we have here. Okay, so and that will, the whole thing will reappear in every dimension. So we're still interested in limits of sequences, as well as limits of functions, of a variety of functions we're going to have. But starting with this simplest definition, of simplest case of a limit. We could have, you can imagine you have a sequence of points on the plane or in space, and we have exactly the same questions to ask as before. In particular, remember how sequences, what did sequences lead to in calculus 2? What's the point of sequences?
Just study series.
And which is for, what's used for series?
Oh, I mean, integration?
Integration, integration, what do you mean by integration?
I mean, the Riemann integral is
well, it is a sequence. It is a limit of Riemann sums. Right. Even though the limit is really more complicated than that, because Riemann sums they're not necessarily sequences, unless you limit yourself to continuous functions. Then yes. But what I was aiming at was primarily the Taylor series. Taylor series is the real big purpose. Taylor series and approximations in general. So other series such as Fourier series would approximate functions, and then you can do integrate or differentiate or whatever, solve all kinds of problems if you know how to approximate functions. So this is also, so we need this to approximate functions of many variables. So either it is parametric curves, or it is a function of two variables, or anything that will come up. We still need all the calculus 1, but also calculus 2 sequences in series. Okay, so that's why that will have to reappear later in this in the same point being geometry and algebra will have to be developed. So that's just the point that we will why we're going to do it this way. But other than that, we will just we'll put the calculus aside for a short while, and let's just look at geometry and algebra of these spaces. Okay, so we are moving on then to well, actually there is a we two-dimension too, but there is another item here that just in case that's neither algebra nor geometry, and that's this one. Technically, it is you probably can call it order relation between numbers. Something that that is does not exactly fit into either algebra or geometry. In mathematics, if you're into this kind of thing, some of these things might be studied separately. So I'm studying geometry, I'm studying algebra, and now I might be studying order relations separately. Okay, so now what happens? What happens in dimension 2? So once again, we have the same issue to consider, and that is distance between points. That's all there is. So there is nothing unpredictable here. So dimension 2, and meaning are 2. So P and Q are points. What is the distance? In terms of their coordinates. Okay, so let me try to use this notation. This dpq, d certainly stands for distance, and I'm not positive that's the notation that the book uses, but it's certainly one of the way to do it. Just nothing but the distance between 2 points, and they are expressed in terms of x, y coordinates of P, and say u, v coordinates of Q. Okay, so that is the question. The answer you know. So what's the answer?
You say xp minus xq, comma yp minus yq.
No, the distance, well, what is the distance? Distance is a number. Okay, so I think what you said is like a vector, which is where we're going to get to that, but not a long time from now. There is a specific formula for the distance. It is called the distance formula. Remember what it is?
Square root of xp minus xq plus...
Well, let me use what I have here. So u to v coordinates of q and y minus v. I will avoid a subscript until the very last moment when we write the formula for n-dimensional or 4-dimensional space at least. So that this is still familiar. So this calculus comes from pre-calculus, I suppose. And so it is, and then so for the time being, we're still using x and y. Okay, so to see where this is coming from, it is a good idea to know. So it comes from the geometry of the axes. Okay, so what is this? Distance.
It's the absolute value of x minus u.
That's right. So because this is x, and this is x, and this is u, right? So this is x minus u absolute value, which is incidentally the same as u minus x. Okay, doesn't matter. Okay, and that term goes here, and the second term is this over here. So this is y, and this is v. Okay, and then this is y minus v, which is the same as v minus y, and that term is here. Okay. So how do I justify this transition? So this comes from these measurements, and these formulas come from just previous discussion, right? This is the x-axis. We know how to measure distances on straight lines when you have all the markings provided. So our algebra is taken care of on each of these at the two x's separately, and now we combine them together in this formula based on what? The Pythagorean theorem. So this is the distance. dpq is right here, and as you can see, it's the hypotenuse of the right triangle. Okay, and that there's really nothing else to worry about here. So there you go. Certainly, you can see the picture is it does not reflect the possible all possible outcomes, but it will be the same. So P higher, but to the left of Q, we could interchange them this way, that way. That doesn't matter. All of this will still work. Okay, it doesn't matter. That will still work, and there will be still the Pythagorean theorem applicable, with one exception, is when when they are on the same line, such as this, technically on the same vertical, on the same horizontal line, P and Q, the Pythagorean theorem technically does not apply because it's not a triangle anymore, right? But on the other hand, it means that if they're located on the same line, it means that x is equal to u, so the first term disappears, and you have dpq equal to simply y minus v. Okay, so it still matches. Similarly, so they will, once again, these are exceptions. Exceptions from the Pythagorean theorem, even though, well, the Pythagorean theorem does say that it's got to be a triangle, a right triangle. Okay, so if it's not a triangle, you can say it is, what we are looking here is you can say it is a degenerate triangle, so a triangle that degenerates into a segment, okay, and it could degenerate into a pair of horizontal lines as well, but nonetheless, it probably doesn't make sense to overstate the Pythagorean theorem. It's good enough as it is. So Pythagorean theorem applies to triangles plus these two exceptions of the possible mutual locations of these 2 points. So either they are on the same horizontal line or on the same vertical line. So distance is, if it is vertical, the distance is x minus, hold on a second. No, that's not what I meant. What I meant is, what I meant is, okay, so this is a P and this is Q, and what I'm saying is x is equal to u, and that's why the first term disappears in the formula. If we have two horizontal located on the same horizontal line, then y is equal to v, right? And so dpq is equal to x minus u. Okay, so it's a match. So either we measure vertically or horizontally, the triangle disappears or degenerates into a segment, but the formula still applies. Okay, because it's kind of becomes the situation becomes one-dimensional. Okay, so that works out just fine. We move on to dimension 3, which is slightly more complicated, but it is the analysis is more complicated than the formula, because you can guess what the formula is after well, if you don't, let me suggest what you could see. So r1 dpq is equal to p minus q, but also you can write it as p minus q squared square root. Why would I do it this way? Just to see, I want you to see the similarity with the dimension 2. So it will be x minus u squared plus y minus v squared. As you can see, you have a square root. In either case, you have a square root, and you have a difference of coordinates squared. Okay, so it just happens that you don't need it in dimension 1 because there's only one term, and then the square and square root result in, read it from right to left, square root of a square is the absolute value. Okay, so that explains the formula, but the point of using there is no point of using this formula that the way I wrote it at top right, But the point is to see the analogy with the next one, and you can predict then what's going to happen in dimension 3 and in the rest of the dimensions as well. So, in dimension 3, what's the formula? Say P is equal to XYZ, Q is equal to UVW. Okay, so what do? We 3 coordinates instead of 2, we add them together, and then still the square root. So x minus u, so every time we add an extra term. Z minus w. Okay, so that's exactly what has happened. This is the extra term as we move this way. And this one was also added when we moved from dimension 1 to dimension 2. We added an extra term inside the square root, and then we added one more, and then let me do R4. So P is equal to, say, x1, x2, x3, x4. Okay, and Q is equal to, let's say, u1, u2, u3, u4. Okay, so then distance between P and Q will contain 4 terms, u1 square root and 4 terms, and x1 minus u1 squared, x2 minus u2 squared, and you can see how it becomes repetitive in a good way. Well, in mathematics, repetitive is good because then you don't have to think as much. Okay, like this. Okay? So G stands for, so P and Q, see how I am using the, this notation, very compact notation on the left, P and Q, and then there is possibly a long formula because it's expressed in terms of all the coordinates. Before we actually, we still need to justify it because at this point this is nothing but thinking by analogy. So it seems that we add an extra term every time, so let's keep adding it and see if it works out. It does work out, but let's take that all the way through. How would you write a formula in dimension n? Use your skills from calculus 2.
So we could could put the summation sign under the
Right.
under
Yeah.
the
So remember the sigma notation. So we'll make it way more compact, and then repetitiveness will be taken taken advantage of. So okay. So what do I have here? Square root of what? Instead of 4 terms, I have n terms. Okay, so sigma
1 to n.
from 1 to n, say k from 1 to n.
X.
Yeah.
Oh yeah, xk. X sub k
Yeah.
minus u sub k.
Square. Okay, so so it doesn't look as bad anymore. Certainly, if you were comfortable with the sigma notation, then this is really no big deal. But we're not going to be using a lot of these formulas. As a matter of fact, we will rely on. Very often we will going to rely on rather than properties of these functions of these the distances rather than the actual formulas. The point, but let me justify this one because we cannot really. R3 is still this space. It still makes sense as a real life environment. So we need to justify it. It's not very hard to justify using the Pythagorean theorem again. So let me, to make our life easier, how about I will simply compute the distance from the origin to to point P with P equal to, with coordinates x, y, z. Okay? So I have a point x, y, z here somewhere. Here, P, x, y, z. Okay? And then all we need to do in order to justify the formula is to see all the right triangles that are available here, and all we have to do is just to look at the projections of this point on the planes and on the axis. Okay, so I'll start with the planes, and I'll go initially I will go down on the xy plane. Let me mark x, y, z. So the coordinates of this point are it is x, y, z, and then we sort of cancel the z. So it will be simply x, y. Okay, and then I can go on, and I can, so I'm going down from my point, I go to the left to find x. So now I'm entirely in the xy plane, and the coordinates of this point are x and y. Okay, so then these are the and then I do the same with the rest of them. Okay, let me pick the green one. So I'm going to the xz plane. Okay, and this is the plane. This is the point. It has coordinates xz. And once again, we're building a little cube here. Not a cube, a box. So, a box with dimensions x, y, z. Okay, so finally the last one, I'm going to go towards YZ plane like this. Okay. I'm going out of the room here. Where is this? Okay, so I'm going towards the YZ plane. This point on the YZ plane has coordinates YZ. Okay, and then this is connects the box into one. Okay, so xz over here, and the red one is still, this one is still xyz. Okay, so we build the box, and as I said, all the sides have just lengths xyz. Okay, and then what is that we're talking about? We're talking about this. From the origin to the point P, x, y, z. Okay, so how do we see it? How do we solve the problem? We see a triangle, so let's start here. Okay, so we cut the triangle in the xy plane, and look at what is the length of this? What's the length of this?
Square root of x squared y squared.
That's right. So let me plot it. So it looks like this. This is y, and this is x. So this is x squared plus y squared square root. Okay, and then look at it. So that's one triangle that we utilized, but then there is the other triangle that actually what our actual interest is the one standing on top of colors. So suppose this is what I'm talking about, and on top of the yellow line there is another triangle standing, vertical one, with the purple top or purple slope, the one that we're interested in, right? So this is what our interest is now. So, and that triangle has, let me plot that triangle separately. It will have this, and then it has the yellow line that we just found, and it has this line that we need to find. So this is still d cubed that we need to find. This one is x squared plus y squared square root. And what is the other side? This one? It is the vertical. Everything everything up to this point was within the xy plane, and now we make a step to z, and then once again we have another right triangle, and it might need an explanation why this is a right triangle, but let's just take that for granted. And then we're using the Pythagorean the second time, so Pythagorean theorem once, and now Pythagorean theorem twice. Okay, so it will be, so dpq, I'm sorry, this is 0p. That's where we're going from 0 to p. So the 0p is what? The square root of x squared plus y squared squared plus z squared. Okay, and then we end up with what we wanted to have it anyway. Okay, so, and we have the distance formula. So that justifies our conclusion. It is harder to justify the rest of the formulas such as this. So why? So this question is why, and the answer is because of the Pythagorean theorem used twice. Okay, here y in dimension 4 and higher is not as easy to justify. The best for dimension 2, the best way to justify is to say that at least if we are in the four-dimensional space and we decide that how about we drop down to one of those three-dimensional slices. Where is that? Where am my slices? So we have slices so these are the slices for the three-dimensional space sliced into two-dimensional sheets. Okay, the four-dimensional space is sliced into three-dimensional sheets, if you like. But the point being is that the geometry, the formula should be the same if we are going to one of its copies of our three contained in it. So, meaning that, for example, I simply put this equal to 0, okay? So I drop out of, it is still four-dimensional space, but we are limiting ourselves to what's happening on the in the three-dimensional space with x1, x2, x3. Okay, and as you can see, what happens to the formula on the right if these two are zeros? What happens to the formula?
What was the question?
So we are in R4, and what if just happens that P and Q are located within a three-dimensional space, which we acquire by setting the last coordinate equal to 0. So if all the coordinates of all points that we care about have the fourth coordinate equal to 0, then there are only 3 degrees of freedom, and we kind of in a three-dimensional situation. And then the question is what's happening to the formula. You can see what happens. What happens to the last term? It disappears, and we have the exact formula from the previous case. So that's at least a justification. We can do no matter that these don't have to be zeros. They could be, as long as these two are equal to each other. The last term is is 0, and we are in the, once again in a three-dimensional situation. We can drop this one, we can drop any of these coordinates, and every time we'll have the same situation. One of the terms over there disappears, and we have 3 terms, and the formula, the three-dimensional formula applies. So at least that's the best we can do for now to justify the four-dimensional formula is just to refer it, just making sure at least that the three-dimensional situation is not lost. It's still there. So R3 is still inside of R4 as one of those slices. If you can imagine a three-dimensional slice in the four-dimensional space. Okay. Okay. So I also mentioned that, and that's the next stage. Is what's important is about important facts about dpq. that are equally applicable to all dimensions. That would make our life so much easier if we can just have those. They are fairly simple. For example, it is larger than or equal to 0, always. First property. And to begin with, so you can see square root, sum of squares and then square root. Okay, so it cannot be negative. But also there is more to it. dpq is equal to 0 if and only if p is equal to q. So if these are two different points, the distance is positive. It cannot be 0. If you look carefully at the formula, unless all of these pairs are equal, these are equal, these are equal, those are 4 equal, the number will not be 0. And vice versa. If there's a difference, you will end up with a positive number. So the only possibility when the distance is 0, only when it is the same point. The distance from the point to itself is 0, and otherwise this is impossible. So that's property number 1. Property number 2 is dpq is equal to dqp. Kind of obvious. And certainly the formula is symmetric. So those differences, even though I subtracted x minus y, x minus u over there, but they can be reversed. They can be reversed, and the result will be exactly the same, right? So that applies to all dimensions. Geometrically, these conclusions are very, very transparent. If we're talking about distances, then of course the distance cannot be 0 unless it is the same point. And also measuring distance from P to Q or from Q to P is the same, but it turns out that even when we define distance in a manner that is abstract, just a formula, that's it, we cannot see the space, these properties are still satisfied, just looking at the algebra. The more interesting property is this, dpq plus dqs is less than or equal to larger than or equal to. Larger than or equal to d what? So this is the first term over here. This is the second term from Q to S. And what? What? PS. It is larger than or equal to the last one. Okay? It's called the triangle inequality. It is equally applicable to dimension 1. There could be no triangle there in dimension 1, but it still works. If we talk about real numbers, so this is P, this is Q, and this is S. If you try to do just subtracting absolute value, it will be Q minus P plus S minus Q will be larger than or equal to S minus P. Okay, so that's in dimension 1. It is still applicable. Okay. Secondly, what about dimension 4 and higher? How do we justify this formula? Well, first of all, we do this we know from Euclidean geometry, right? So the shortest distance between 2 points is a straight line. That's exactly what it says, right? That is the straight line, and the distance is the shortest than if you go any other way. So whatever point Q is, you cannot do better than straight line. Okay, that's what we're saying. Why? How do we justify this for dimensions beyond 3?
Can we just show that it holds by carrying out some computation?
We could, yeah. So proof is computational. But you can justify it if you don't want to do it. It's a little bit heavy on computation, not hard, but heavy. But you can justify it informally by saying simply that it is well, 3 points. 3 points. Let's say we're talking about three-dimensional space. if 3 points define what they define. They define a plane. It doesn't matter what the dimension of the whole space is. If we pick only 3 points, they define a plane, and we are back in R2. So this is inevitably like this. This is a copy of R2. Okay, so if we are only looking at 3 points, we are not, no multidimensional features will necessarily come up. In this particular case, all we do is measuring distances, and we're measuring distances within this plane. Okay, so that is very helpful observation that saves a lot of time for us in the future when we deal with either distances, points, or vectors. You have 3 points, or you have 2 lines, for example. Once again, you have 2 lines. If they intersect, they define a plane and no more. And once again, we're staying within that point. Okay. So, but once again, what I said is not a proof. The proof is actually you have to do the computations. Okay. So these properties can be freely used without referring to the dimension of the space. Okay, now we are moving towards algebra. So we already saw algebra in R1 with real numbers. So simply x minus y. We needed x minus y in order to compute the distance. Beyond that, in R2, we might need algebra in order to deal with vectors, and in particular, as I mentioned before, we're gonna also look into angles too. Well, actually, let's start with the R1. There are angles. It seems like there are no triangles in R1, so there seems to be no angles, but there are actual angles. If I have 2 points, say P and Q, then I could speak about the angle between OP and OQ. Exactly. So what are they?
OQ.
OP and OQ. In this particular case, it is indeed 180 degrees, so it is possible, and it is possible if I put, instead I put Q over there, on the right, what's the angle then? So if my P is still there, and Q is also to the right, what's the angle? 0. So these are the only 2 possibilities, but it's still you want to, in an algebraic way, recognize whether the 2 points are pointing in the same direction or in the opposite direction. So it can be done as well. So we'll do it next time.